All right, so today we're talking bisectors of a triangle. There's quite a few new terms today, so make sure you have your notes out and ready because a lot of the terms over the next two sections are going to be very similar, so it will be very, very helpful to have them in your notes and just at your fingertip so you can reference them quickly on tests, quizzes, homework, etc. So, first word, perpendicular bisector. That is a line that cuts a segment in half at a 90-degree angle. So, when we think perpendicular, always think 90 degrees. And then bisector, bi means two, so it means it's cut in half. So perpendicular bisector, a line that cuts another segment in half at a 90-degree angle. Concurrent lines. So concurrent lines are two or more lines that intersect at a single point. So this picture below, this one right here, that is a set of concurrent lines. So it's anytime you just have two or more that connect at the same point. And then the point of concurrency is the point where the concurrent lines intersect. So in this case, it's point P right here in the middle, all happily getting cut by all three of those lines. Onward and upward. So our next word that we have, which I skipped a slide, is circumcenter. So the circumcenter is the center of a triangle. Triangles. Oh, wow. That was really good wording by me. Wow. So what the circumcenter is if you drew a circle that held all three of the vertices, the circumcenter would be the center of that circle. The center of a triangle, circumcenter. I believe the word I was looking for there would be circumference. The center of a triangle's circumference, which I probably spelled wrong, but that's fine. So you find this at the intersection of all three perpendicular bisectors. So if you take each side and you draw in a perpendicular bisector, so 90 degrees from the midpoint, where those three lines intersect, that would be your circumcenter. That's just great wording. I love that. The center of a triangle's circumcenter. It's just not a real thing. All right, moving on. So the incenter is the intersection of the interior angle bisectors. So if you draw in an angle bisector, so just a refresh, an angle bisector is a ray or a line segment that bisects the interior angle. So it cuts the angle in half. So each individual piece is going to be the same angle measure. So like if we're looking at angle C over here, it might be 20 degrees and 20 degrees. So it cuts that original 40-degree angle in half. So the incenter is the intersection of the interior angle bisectors. And the cool thing about the incenter is then we have these three line segments in here, and all of these end up being the same length, which is really cool. So we'll talk more about that later. So as we continue on, we get to our theorems. Yes, I love theorems. Let's go. So perpendicular bisector theorem. What this says is if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of a segment. So this makes sense if we think about it. So if we have this line AB right here, and then we have a perpendicular bisector going up and down, then any point on this perpendicular bisector is going to be the same distance from both A and B, which that would make sense because if you think of like, I don't know, to me I think of it like a slingshot almost, that bisector. You pull it back and then it's going to go forward. So it's going to be the same distance because it started at the same relative position on the original segment. So if it started in the middle and then it stretched right along that line, then you're going to be pulling equally with both of those. So AC and BC would be congruent by this perpendicular bisector theorem. So the converse of the perpendicular bisector theorem says that if a point is equidistant from the endpoints of a segment, then it is on a perpendicular bisector of the segment. So if we have a point like E, so we have a point like E, and it's the same distance from A and B, then it is on a perpendicular bisector, which once again does make sense by the same reasoning. So it's just the backwards of the perpendicular bisector theorem. Moving on. So from the information in the diagram, or find BC, sorry, I kind of jumped the gun a little bit there. So right away, based on our diagram, if we look at AB, I need this to be a little bit bigger. So AB, that line that I made in bold blue, and then we have DC, which is a perpendicular bisector here, because it cuts AB in half, and then we can see that it intersects at a 90-degree angle, which by definition makes it a perpendicular bisector. So, and we're supposed to find BC. And right away, we know, based upon our perpendicular bisector theory, that if we have a perpendicular bisector, then the distance from the points are going to be equal. So on the original segment, we have A and B. So the distance from point C that is on the perpendicular bisector, the distance from C to A is going to be the same distance from C to B. So we know BC is 8.5. Woo woo. Cool. So continuing on, we're supposed to find XY, which for this, we're going to use the converse of the perpendicular bisector theorem, because in this picture, we can see that we have a 90-degree intersection here with our original segment, XZ, and then we also have an equal distance between W and X and W and Z. Those are the same distance, which means that this is a perpendicular bisector, this WY line, which means YZ and XY are the same distance, which means line XY is going to be 6 as well. Lovely. Continuing on. Yes, now we get into our algebra. What? So they want us to find PQ, which in order to do that, we have to figure out if we can set these equal to each other, which I can tell we can. Because, so if we look at PR as our original segment here that I'm highlighting in more blue, we can see that it is bisected by point S, and point SQ intersects it at a 90-degree angle, which by definition makes it a perpendicular bisector. And since it's a perpendicular bisector, we know that point Q, which lies on that perpendicular bisector, is the same distance from R as it is from P, which means 3x plus 1 is equal to 5x minus 3. Now that we know that, we can set ourselves up a nice little handy-dandy algebraic equation, and we can solve that thing. So I'm going to add 3 to both sides. At the same time, I'm going to subtract 3x, which leaves me with 2x equals 4. Then I divide by 2 on both sides to keep the equation balanced and happy, and we get x equals 2. But we're not done. We know x equals 2, but they wanted to know what PQ was. So now I got to plug in my x equals 2 back to this original equation. So I'm going to write 3x plus 1, but I'm going to substitute in the 2 for the x, which leaves me with 3 times 2 plus 1, which would be 6 plus 1, which would be 7. So PQ equals 7. Yay! Continuing on. So these are the questions that I will have you do on your own in the Zoom. I'm just going to circle the answers here. It's 9.2. TU is going to be 4. It's going to be 8. All right, now we get into the circumcenter theorem. So what the circumcenter theorem says, the perpendicular bisector of a triangle intersect at a point called the circumcenter that is equidistant from the vertices of the triangle. So the circumcenter, point P here, is going to be equidistant from the vertices of the triangle, which means this, and this are all equal. Now, me seeing that 3 segments are equal, that rings in my head, you know what? There's probably going to be algebra problems on this, where I have to set 2 things equal to each other. So, in this example, like we said, PB is equal to PA, which is equal to PC. They're all congruent to each other because point P is the circumcenter, where those perpendicular bisectors intersect. Moving on. So, circumcenter theorem. Oh, we already said that, didn't we? Just said this. Why are there 2 slides for that? That's dumb. Oh, this has the proof. We don't do proofs here. Paragraph proofs are dumb, and I don't like them. So, continuing on. So, a triangular-shaped garden is shown. Can a fountain be placed at the circumcenter and still be inside the garden? So, by the circumcenter theorem, a point equidistant from 3 points is found by using the perpendicular bisectors of a triangle formed by those points. Okay, so right away we have no measurements or anything, so we're just going to kind of eyeball this. So I'm going to say that is one of my perpendicular bisectors, because that looks pretty even. And then this one would be kind of like that. That would be about a perpendicular bisector. I know this isn't perfect, but bear with me. I guess that would be like my third one, which is actually pretty close to intersecting. So I'll give myself credit there for mediocre art skills, and I'm kind of happy with that. So I would say probably can't be built using this obtuse triangle, but let's double check. So, let's just appreciate real quick how similar mine and theirs looks. As I flip back and forth really quick, you can hardly tell that this is the one I drew. Yes, this one with the perfectly straight lines and the 90-degree angles. This is the one I drew. So, they say copy this, use a ruler and protractor to draw. Why do we need that when we have Mr. Wright's art skills? So, their answer is no, the circumcenter of an obtuse triangle is in the exterior of the triangle, which checks out. So, the circumcenter of an obtuse is on the outside. The circumcenter of a right triangle is going to be on the hypotenuse. So, obtuse, exterior, acute, interior, right is going to be on the hypotenuse, or the longest side. I don't think you'll ever need that information, but I don't know, it's a fun fact. Maybe one day you'll get on Jeopardy and win some serious money with that, and then you'll come back here and split it with me, because that's the only fair thing to do. Especially since my YouTube channel's not taking off, so, you know, all help is appreciated. So, a triangle used to rack pool balls is shown. Would the circumcenter be found inside the triangle? So, let's do the same thing. Let's show off my art skills again. So if I do 90 degrees about right in there, then we do 90 degrees about right in there, and then I think 90 degrees would be about right through there, which is once again actually pretty good. All those even intersected. So I would say, yeah, it's going to be in the middle. And it's an acute triangle, so we know it's going to be on the interior. So, yeah. Cool. So, continuing on, angle bisector theorem. If a point is on the bisector of an angle, then it is equidistant from the sides of the angle, which makes sense. So, if we have an angle bisector here, like BF, then it's going to be the same distance from each of these lines. Yeah, it's like the definition of a bisector. It's equidistant. So if I drew a point here, it's going to be the same distance from both of these lines, pretending my art skills are even halfway acceptable. But so converse of the angle bisector theorem, what this says is if you have a point and it's equidistant from the two sides of this angle, then you have an angle bisector. So it's just the opposite of the angle bisector theorem, which is lovely. So now we are supposed to find dB. So right away, what I see is they have these two little hash marks in here, which means these two angles are the same, which means AD is going to be an angle bisector, which also means that DC and BD have to be congruent, which means DB is 5. Yay. All right, now what about QS? Okay, so we have kind of the same situation, same drawing here. So we have two angles that are the same, which means this lovely line is our angle bisector, which means that QS and SR are congruent. So 4x minus 1 is going to equal 3x plus 2. Now, I go about solving this, do a little solvey-solve, and I end up with x equals 3. Woo-woo. And continuing on, this is one that you'll do on the Zoom. However, I will give you the answer right here. Super secret time. It's C. Mainly because 2 congruent angles means that's bisector, which means these two have to be the same, which means this is 11. Continuing on, find the measure of HFI. So we have two congruent segments here, so that means h is equidistant from both of these individual legs of this angle, which means that since this is 30, this also has to be 30, which means the answer is B. Continuing on, once again, same situation as before. We have two angles that are the same, which means this is an angle bisector, which means those two are the same, which means we'd have to solve these, or we'd have to set these equal to each other and then solve these, which would look a little bit like that. And then we would end up with x equals 7. All right, so in-center theorem. What in-center theorem says is the angle bisectors of a triangle intersect at a point called the in-center that is equidistant from the sides of the triangle. So the in-center is equidistant from all the sides of the triangle. And of course, that's like the shortest distance to the sides, which is always at a 90-degree angle. That's why you see all these little 90-degree signs showing up here. And then all three of these segments are equal to each other, like they show down there in the example. All right? So, onward we go. Find ST if S is the in-center. So if S is the in-center, oh, hang on, did we skip something here? No, we didn't. We're good. Okay. So find ST if S is the in-center of MNP. Okay, so S is the in-center, which means that ST, SU, and SR are all congruent. Now, right away, what I'm seeing here is we only have two side lengths. So we have a side length of 8 and we have a side length of 10. But where we're in luck is those make a right triangle. And when we have a right triangle, we can use Pythagorean's theorem. So I'm going to redraw this triangle really quick just so it's a little more viewer friendly. So let's erase that. I don't like how that bottom line turned out. There we go. Perfect. This was 10. This was 8. This was unknown. So if I call this A, B, C, what Pythagorean's theorem says is A squared plus B squared equals C squared. And C squared always has to be the hypotenuse, or the side that's opposite of the 90-degree angle, because it's the longest side. So that's just how Pythagoras worked it out. It's how it operates. So now my next step, I'm going to want to substitute in these values into Pythagorean theorem. So I'm going to say A squared, or 8 squared, plus B squared, which I'm going to call X, so plus X squared, equals C squared, with C being 10, so 10 squared. Now I'm going to start simplifying, so I have 64 plus X squared equals 100. Solving this for X, so we end up with X squared equals 36. Now this last step, to get X completely by itself, we have to take the square root of both sides, and the square root gets rid of this squared over here. So we're left with X equals the square root of 36, which is, of course, plus or minus 6. But since we're dealing in length here, you can't have a negative length, so we're just going to say 6. All right, so if X is 6, we know then SU equals 6. But that's not what they wanted. They want ST. Well, good news is we know SU and ST are congruent, so we can say confidently that ST also equals 6, which makes us very happy. Continuing on, They want us to find the measure of angle SPU if S is the incenter of triangle MNP. So they want us to find SPU. Let's find SSPU. So this little angle right here is what we're looking for. Now, interesting thing here, we know all triangles, the interior angles add up to equal 180 degrees. Now, the tricky part here is we don't have all the angles for any single triangle, but we do know that these are angle bisectors, which means that SMR, or 31, is congruent to TMS. That also has to be 31, which means this whole angle here is going to be 62 degrees. And we can do that same thing up top here. We have N, so we have TNS and SNU both equal 28, which means if we combine them, we have 56 degrees, which we could use if we trace our large triangle here. Just pretend all this middle stuff doesn't exist now. We could use that to figure out what this big green angle is over here on the right-hand side. So let's go ahead and do that. So we know, I'm going to use red. So we know 62 plus 56 plus something, I'm going to call that something x, equals 180. So now if I start solving this, I get 118 plus x equals 180. I'm going to subtract 118 from both sides, which will, of course, give me 62. So I know x equals 62. Now, that's for the big green angle down here that I just colored red because I can't select green. There we go. So this big green angle right down here that I just colored in completely because coloring is fun is 62. However, they wanted the measure of angle SPU, which is only this little chunk, which we know SP is an angle bisector, so we know this chunk and this chunk are equal and they add up to equal 62. So we know, I'm going to call this y. So we know y plus y is going to equal 62, or 2y equals 62. So if we solve that and divide by 2 on both sides, we would find out that y equals 31, also known as the measure of angle SPU equals 31 degrees. All right, I know that was a very involved problem. And to be fair, that was really just one of the ways you could solve it. There are a couple other ways, but like just an example of another way, we know this right here is 28. We know that's 90. So we could find out that this angle right here is, what would it be? 62. So we would know this is 62. That's 62. And then this would be 62, which would mean if we added 62 and 62, we would have 124. 62, 62, and this angle have to equal 180. So we would know that would have to be 56. Hang on, why didn't that work? That should have worked. Did I mess up my math somewhere? 124, which would be 56, 56, and then never mind, I guess that's the way you have to solve it. of that. What is going on? Why did that not work? So those are all bisectors. I don't know why that didn't work, but it's going to bother me. I'm going to have to explore that more. So anyway, last problem before my brain completely melts. Find the measure of GF if D is the incenter. So if D is the incenter, then of course these three lines should be the same. And we're supposed to find GF, which is going to be 8. Essentially, you'll have to do Pythagorean theorem there again. So we would do 13 squared, which would be 169 minus 25 equals... Oh, I'm sorry. I lied. It's not 8. Because that's going to equal 144. Then we would take the square root of that, which would be 12. I lied to you. I sincerely apologize. I also lied about that being the last problem, apparently. So we need to find BCD. BCD, which would get, this side would be 58, 70, which means that would be 128, which would mean we'd need 52, right? Yeah, 52. All right, cool. I just got to look at this one more time. You guys can stop watching the video. I'm just continuing in case I solve this. So I cannot figure out for the life of me what went wrong with that. So that should have been... Sorry, this one. So that would have been 56. So that would have been... would have needed to go to 62, right? So it would have been 62. That would have had to be 62. Which would mean... which means that last one would have to be 60. 56. Yes, that would have to be 56. And then... Oh. No, that doesn't make sense. This does not make sense. This is stupid. Yeah, so that would have to be 56. I am baffled. I am baffled. The answer should not be that. The answer should be... it shouldn't be 31, it should be 56. should be 34, shouldn't it? That's garbage. SPU should be 34. Because then 62 plus 56 would be 118. For those two, 180 minus 118, which would be 62, right? Oh, I'm absolutely brain busted. This is ridiculous. Because that would be 90. 90 plus 56, which would make that angle 34. So that would have to be 34. So let's have to make this 56. They totally messed this up. They messed up their numbers. This is ridiculous because there can be two different answers. They just made this triangle not work.